Option is not there. Yeah, recording is there. Right. Now, screen is visible?
No, sir.
Yeah.
No, no, sir.
No?
No, sir. Yes, sir.
Now?
Visible, sir.
Is it okay?
Yes, sir.
Yeah. Now see, higher order differential equations. Generally, nth order differential equation representation is this equation 1. Equation 1. And here we represent the operator form of equation 1. How we can represent the nth order differential equation in operator form. For that, we introduce a one letter capital D. D stands for derivative with respect to x. First derivative only. Remember, D means first derivative, d by dx with the differential operator. This is operator. Then this d square. D square means it represented by double derivative, and so on. Nth derivative is represented by d power n dx power n. D power n by dx power n. Okay, this is the operator. Then equation 1 can be written as, then equation 1 can be written in operator form as, see, I will write here. First term is what? A naught x into nth derivative, d power n nth derivative of what? Y. See this part. This is this one. D power this part is d power n into y. D power n into y. So I will write that d power n into y plus a1 x into n minus 1th derivative. Next, a2 x into n minus 2th derivative. This is y, and so on. Lastly, what? A n minus 2 double derivative plus a n minus 1 first derivative plus a n y only equal to r of x, equal to r of x. Then in this entire y is common. Then I can write a naught x into d power n plus a1 x into d power n minus 1 plus a2 x into d power n minus 2, and so on. A n minus 2 into d square plus a n minus 1 into d plus a n into y here. This I'm taking this y outside, this y outside, into y equal to r of x, into y equal to r of x. This is equation 2. Equation 2 is the operator form of equation 1, is the operator form of equation 1. Operator form of equation 1. Then one more point. If a naught, a1 and so on, an are constants, not functions of x, are constants, then equation 1 is called, if all are constant, equation 1 is called constant coefficient linear differential equation, linear nth order, constant coefficient nth order linear differential equation, Then what is equation 2 becomes then operator form, just it is a constant. So a naught into d power n plus a1 into d power n minus 1 plus a2 into d power n minus 2, and so on, plus a n minus 2 into d square plus a n minus 1 into d plus a n into y equal to what? R of x, equal to what? R of x. This is equation 3. This is operator form, and this can be written as, All of you, this is important. This can be written as, see, what is this? A0, A1, A2, all are constants, and D stands for derivative. So this entire equation 3 can be written as function of D into y equal to R of x. Function of D into y equal to R of x is the operator form of constant quotient differential equation. Constant quotient nth order linear differential equation. Nth order linear differential equation. This is the first basic concept. Once again, let me explain. The nth order linear differential equation form is equation 1. Just what I have written, some function of x into nth derivative, function of x into n minus 1th derivative, function of x into n minus 2th derivative, and so on, equal to some function r of x. And to represent it in operator form, let us denote capital D as the derivative d by dx. Then obviously d square means double derivative, d power n means nth derivative. So equation 1 can be written in the operator form in this manner. Equation 2. When this A0, A1 and AN all are constants, then equation 1 is called constant quotient linear differential equation. And what is its operator form? Exactly this. Since A0, AN, A2 all are constant, this entire bracket can be treated as function of D into y equal to R of x. So whenever f of D into y equal to R of x is given, means what? It represents constant quotient differential equation. Constant quotient differential equation. For example, see, if I write some x square into d square y by dx square plus 2x minus 1 into dy by dx minus 2y equal to e to the power of x. It is a second order equation. Is a second order differential equation. Second order differential equation, but not constant quotient, because derivative coefficients are what? Variables. Not all are constant, variables. Okay, this is one. And second one, if I write, for example, d cube y by dx cube minus y equal to sine 2x. Yes, what is its quotient? The third derivative quotient is 1, y quotient is 1, is constant quotient third order differential equation. So how to write this one? This is in operator form, d cube y minus y equal to sine 2x. So I can take y common. So d cube minus y equal to sine 2x. This is operator form. F of d into y equal to r of x. Okay. Now, for this next point is, for nth order differential equation, there exist n solutions. For nth order differential equation, there exist n solutions. That means for the differential equation, for third order differential equation, there exist 3 solutions. Second order differential equation, there exist 2 solutions, like that. Then let f1x, f2x, and so on, f1x be the solutions of, be the n solutions of equation 1. N solutions of equation 1. Then one definition to define whether these solutions are independent or dependent. For that, there is one definition we have to give, that is a linear combination. I told this definition, linear combination, in vectors, eigenvectors. Okay, linear combination of functions. The linear combination of n functions, linear combination of n functions f1x, f2x, and so on, fnx is defined as c1 constant c1 into f1x plus c2 into f2x plus and so on cn into fnx, where c1, c2, and so on cn are constants. Do you remember in matrices I told you one concept? What is that? In matrices, linearly independent and linearly dependent vectors. Do you remember? Okay, what is there? C1 x1, x for capital X1, C2 x2, and so on. Just if I write C3 x3 equal to 0, then it gives what? C1 into some vector, right? Plus C2 into another vector. To decide whether the given vectors are linearly independent or dependent, what we did, this is called linear combination. Linear combination of three vectors equal to 0. That means 0, 0, 0, right? Then you will get what? You will get equation, system of equations in C1 and C2, right? C1, C2, C3. Some another equation. Got it? Do you remember? Linearly independent, dependent eigenvectors. To decide whether the vectors x1, x2, x3 are linearly independent or independent, we consider linear combination of these three vectors, that is c1 x1 plus c2 x2 plus c3 x3 equal to 0. Then if I substitute the vectors, and I will get system of equations. System of what equations? System of homogeneous equations. Right? Then if I solve this, if I get zero solution, then x1, x2, x3 are what? All are 0 means linearly independent. If at least C1, at least one Ci, if at least, not all are 0, at least one Ci not equal to 0, then vectors are what? Linearly dependent. This is the concept. In vectors. Now same logic here also. Let us, using this linear combination, how to decide whether the given vectors are given solutions are linearly independent or dependent. The first definition, linearly independent. I will give both definitions simultaneously. Linearly independent and dependence. Solutions. Okay. Now you consider consider the linear combination. Consider the linear combination of n solutions. Solutions are nothing but functions of x, right? So I will write functions. What are those functions? f1x, f2x, and so on, fnx. Consider the linear combination of the solutions. What is that? C1 into f1x plus C2 into f2x plus and so on, Cn into fnx. Now take C1 into f1x plus C2 into f2x, like in matrices. Equate this linear combination to 0. Then, okay, if in the above equation, now this is equal to 0 means equation. In the above equation, all Ci equal to 0, all ci equal to all ci equal to 0, then functions are or solutions are all ci equal to 0. What is here? Linearly independent. Here also same thing. All ci equal to 0, then functions are linearly independent. Linearly independent. If at least one ci not equal to 0, at least one ci not equal to 0, then functions are linearly dependent. Linearly dependent. This is the original definition. All ci equal to 0, linearly independent. At least one ci not equal to 0, linearly dependent. Linearly dependent. Then how to find? For example, see, just I will give one example. Check whether the functions are, you take this example. Yeah. What are the functions? X square minus 1, 3x square, and 2 minus 5x square. 2 minus 5x square. This is function f1. f1x equal to x square minus 1. f2x equal to 3x square. And f3x equal to what? 2 minus 5x square. What I have to consider? Take c1 into f1x plus c2 into f2x plus c3 into f3x. This is linear combination and equal to 0. Then what I'm getting? This is c1 into x square minus 1, c2 into 3x square plus c3 into 2 minus 5x square equal to 0. I'm not getting any system of equations like in matrices to solve the system for the solution c1, c2, c3. Okay, then how to solve this? Now let me take x square common here. c1 plus 3c2 minus 5c3 into x square plus, what is the next one? I think remaining are constants. So what are the constants here? C2, there is no constant. Let's 2c3 minus c1 equal to 0. Equal to 0. This is true for all x. This is true for all x. Now, what we have now? We have, when they say equality is true, equal to 0 means 1, it will be true. This must be true for all x means what? This coefficient must be 0. This coefficient must be 0. So then we have c1, then only it is satisfied. Minus 5c3 equal to 0. 2c3 minus c1 equal to 0. Done. From this, what I'm getting? c1 equal to 2c3. c1 equal to 2c3. Substitute here. What I'm getting? This is 2c3 plus 3c2 minus 5c3 equal to 0. So this is 3c2 equal to 3c3. c2 equal to c3 I'm getting. c2 equal to c3 I'm getting. Right? Okay. Then when c3 equal to this one, c1 equal to c2 equal to c1 equal to 2c3 and this one c1 equal to 2c3 and what is c3 equal to c2? c3 equal to c2. Now is the values are zeros? Values are zeros?
No.
No. Therefore clearly not all ci equal to 0. Clearly not all ci equal to 0. Not all ci equal to 0. Therefore given functions are what?
Linearly
Given
dependent.
functions are linearly dependent. Linearly dependent. But see, these are easy functions. I have considered once easy functions, so that I can decide whether the functions are dependent or independent. But complicated functions are given. Then how to decide? How to decide whether the given functions are linearly independent or dependent? Okay, the general rule. Working procedure, you say. Working procedure. to check whether the given functions are linearly independent or linearly dependent. Linearly independent or linearly dependent. For this, again, for this, there is one property, Wronskian. Spelling is what? Wronskian. W-R. Wronskian. Okay. What is the definition? The Wronskian of n functions, f1x, f2x, and so on, fnx, is defined as what is a Wronskian? This is represented by W. f1, f2, and so on, fn is equal to, first write the functions f1, f2, and so on, fn. Then their derivatives, first derivatives, fn dash. Next, their second derivatives, f2 dash, fn double dash. And lastly, you write n minus 1th derivative. You write n minus 1th derivative. f1 n minus 1th derivative, f2 n minus 1th derivative, fn n minus 1th derivative, fn n minus 1th derivative. It's a determinant. Once again, Wronskian of n functions is, first write the functions in the first row, their first derivatives in the second row, their n minus 1th derivatives in the n minus 1th row. So 1 to n minus 1. This is n minus 1 by n minus 1 determinant. N minus 1 by n minus 1 determinants. Okay. This is Wronskian of n functions. Now, if Wronskian is not equal to 0, if I evaluate this determinant and it is non-zero, Wronskian is not W not equal to 0, then the functions are linearly independent. What is this? Linearly independent. Remember this. Linearly independent. If Wronskian is equal to 0, then the functions are linearly dependent. Linearly dependent. A small, this is one simple criteria to decide whether the given functions are linearly independent or dependent. Linearly independent or dependent. For example, our previous problem, what is that? See, what is that? f1x equal to, just a minute, what is the f1x equal to? What I have taken, x square minus 1. f2x equal to what? 3x square. f3x is what? 2 minus 5x square. 2 minus 5x square. Now, using Wronskian method, we can decide whether these functions are linearly independent or dependent. So, what is Wronskian of function f1, f2, f3 is nothing but determinant of, first write the functions, their first derivatives, and next double derivative. That's it. Double derivative. f2 double derivative, f3 double derivative. So x square minus 1. First function is what? This is equal to x square minus 1. And next one is what? 3x square 2 minus 5x square. 3x square 2 minus 5x square. First derivative 2x, 6x minus 10x. Next derivative 2, 6 minus 10. 2, 6 minus 10. Okay. Now evaluate this determinant, x square minus 1 into minus 60x plus 60x. Is it correct? Minus 60x plus 60x, correct? Minus 3x square into this part, minus 10x square, minus 10x square, plus 10, minus 4, minus plus 10x square. Is it correct? Right. Next one, plus 2 minus 5x square. This is 12x minus 12x. This is equal to this part. First term is 0, minus 3x square. These two also gets cancelled. Any mistake?
So middle term minus 20x plus 20x. Sir.
After minus 3x square.
Minus 3x square into, yeah, this is a mistake. So what is this? Minus 20x plus 20x. Done. So everything is 0, right?
Yes, sir.
0. Since Wronskian is 0, F1, F2, F3 are what? Wronskian 0 means what? Are linearly. Wronskian equal to 0 means, just now I told you, Wronskian 0 means, where it is? Yeah, Wronskian 0 means what? Linearly dependent. Not equal to 0, linearly independent. Now one more example. F1 x equal to x. Yeah. F2x equal to x square. F3x equal to x cube. To check whether these vectors are linearly independent or dependent functions, Wronskian of three functions, F1, F2, F3 equal to x square, x cube. Their first derivatives. Next is second derivative. Now its evaluation. Now x into 12x square minus 6x square. Next, minus x square. Okay, I can evaluate by using first column. That's better. Minus 1 into this, minus 1 into 6x cube minus 2x cube. Next one, 0. So what is this value? 12x square, 6x cube. This is minus 4x cube. This is nothing but 2x cube not equal to 0. 2x cube not equal to 0. Since Wronskian not equal to 0, functions are
Linearly independent.
Linearly independent. Why we are learning this linearly independent dependent functions means, for a constant coefficient differential equation, okay, we must have linearly independent solutions. We require what? We require only linearly independent solutions. For that, we are learning this linearly independent and dependent solutions. Now, how to solve the procedure? You write like this. Let me tell you now, this is linearly independent dependent over now. Working procedure to solve the nth order differential equation. Any doubts? Okay, let's take some problems, assignment problems in linearly independent and dependent. Assignment. Check for linearly independent or linearly dependent. First one, x square minus 2x, 3x square plus x plus 2, 4x square minus x plus 1, e power x sin hx cos hx, x square 1 by x square, 1 cosine x sin x. Next, fifth one, e power minus x sin hx cos hx. And lastly, log x square log x cube. Log x cube. Okay, this is one small topic, linearly independent and dependent solutions. The next one is how to solve higher order linear differential equations. How to solve higher order linear differential equations. Now, and remember, only constant quotient differential equation. First we see how to solve higher order constant coefficient linear differential equations. Okay, now one more point here. The differential equation you write like this. If in the differential equation capital F of d into y, you know operator form this is, right? Capital F of d into y equal to r of x. If r of x is not equal to 0, that means this right side function not equal to 0, then it is called as non-homogeneous differential equation. Not only constant quotient, in variable quotient also same thing, non-homogeneous differential equation. If r of x equal to 0, then what is this becomes f of d into y equal to 0. R of x equal 0, then f of d into y equal to 0 is called homogeneous differential equation. Is called homogeneous differential equation. Okay, these two are the definitions. That means now what is that? In the differential equation, if the right side function is not 0, non-homogeneous differential equation. If the right side function is 0, it is called homogeneous differential equation. This is non-homogeneous. Sometimes it is also called as inhomogeneous differential equation. Inhomogeneous differential equation. Now, first let us solve homogeneous differential equation. Homogeneous constant quotient. Heading: solution of homogeneous constant coefficient linear differential equation. Solution of homogeneous constant quotient linear differential equation. So what is the thing here? Procedure. Consider what is the equation? General form: capital F of d into y equal to 0. Equation 1. Capital F of d into y equal to 0. Equation 1. Okay. Step 1. Consider the characteristic equation. Consider the characteristic equation, or it is also called as auxiliary equation. Characteristic equation or auxiliary equation. Capital F of m equal to 0. Capital F of m equal to 0. The idea is what? This is capital F of d, you know, operator. Just to replace this d by m, and just you write only f of m value and equate it to 0. Capital auxiliary equation, which is an equation in m. Equation in m, right? Maybe, and if this one is nth order differential equation, then this is nth order equation, nth degree equation. Just for your clarification, I will give, for example, d cube minus 1 into y equal to 0. What is f of d here? D cube minus 1. Then what is f of m becomes m cube minus 1. F of m equal to 0. That means m cube minus 1 equal to 0. Cubic equation. Find the roots. Next step. Step 2. Find the roots of f of m equal to 0. Find the roots of f of m equal to 0. Third point. Find the roots of f of m equal to 0. Third point. If in third point, first case, listen carefully. If you thorough with this, then only you can solve the problems. So you have to remember this process. You have to remember this process. How this process is derived, that is the next question. I will tell in the next class. But this process steps are very, very important. Otherwise, you cannot solve any problem. Find the roots of f of m equal to 0. If the roots are real and distinct, if the roots are real and distinct, if the roots are real and distinct, say, I'm saying for m, the roots are m1, m2, and so on, mn. Nth degree. We are considering nth order differential equation. So m roots are. What are these roots? Real. Remember, what are these roots? Real and distinct roots. Then solution is. Solution for what? Y. Dependent variable is y. For m1, you write e power m1x. For m2, you write e power m2x. For mn, you write e power mnx. And for each solution multiplied by a constant, then their linear combination. This is the solution. What is this? For m1, you write e power m1x, or you remember like this better. For m1, you write c1 into e power m1x, plus for m2, you write c2 into m2x, plus for mn, cn into e power mnx is the solution. Is the solution. First case. Now, in second one, if the roots are real and repeated, say, choice is yours. I will take m1 repeated 2 times, m1 repeated 2 times, m2 repeated 3 times, and others are non-repeated. So I'm taking some of them are repeated, some of them are non-repeated, and others are non-repeated. Okay, then what is how to write the solution? Then solution is y of x equal to, now remember all of you, here m1 is not repeated. Then what I have written? For m1, what is the solution? E power m1x is the solution and multiplied by a constant. Same logic here also. For m1, you write e power m1x. m1 repeated how many times here? 2 times. Then instead of c1, previously we have written just c1. If it is repeated 2 times, you write a first degree polynomial as its coefficient, c1 plus c2x. Repeated 2 times means a first degree polynomial. Means what? c1 plus c2x plus. Now m2 repeated how many times? 3 times. First write e power m2x, and if it is repeated 3 times, then its coefficient must be quadratic. That is already c1 c2 over c3 plus c4x plus c5x square, quadratic. Okay, and remaining are not repeated. That means c6 e power m3x plus c7 e power m4x, like that. Lastly, something, see, some constant, some constant into e power mnx. Got it? So remember, the repetition number is very important. If m1, for example, m1 repeated 5 times, then you write e power m1x. And what is its coefficient? 4th degree polynomial. 5 times repeated means e power m1x coefficient must be 4th degree polynomial. That means c1 plus c2x plus c3x square plus c4 x cube plus c5 x power 4, like that you have to write. Any doubts in the repetition? In the repeated
No,
roots, any doubts?
No, sir.
Okay. I will stop here. Okay. In the next class, I will continue.